Hi, everyone, and welcome to this episode. If you're taking the AP Chemistry exam, you might know that you're going to get 60 multiple choice questions and you're going to have 90 minutes in which to do them, which works out on average to about a minute and a half per question. And that can be kind of a challenge because while some questions are going to be quick answers for you, other questions are just going to take a while because there's going to be a lot of words, there's going to be a lot of data to look at. There might be distractors that you have to sort through and try not to be tempted by to pick the wrong answers. So there's a lot going on. And so what I want to do today is to sort of speed run some multiple choice questions relating to thermodynamics. This goes along with Unit 6 of the AP Chemistry curriculum. And so the questions we're doing today are really related to things like heat capacity, enthalpy, and heat diffusion, and things like that. So we're going to get through as many as we can in the shortest amount of time that we can and try to do it quickly. And so let's get started. Our first question today goes as follows. A quantity of 10,000 joules of thermal energy is transferred to 4 different substances. In which of the following experiments would the greatest mass of the given substance undergo the indicated change? Okay, so we have melting ice, boiling liquid acetone. They give us the heat of fusion, heat of vaporization, and a couple of heat capacities. Okay, so remember you have a minute and a half to do questions like this, and you could, if you needed to, take the time to actually do 4 different calculations. Now that will take you some time. But what I'm going to do is I'm looking for the one with the smallest heat capacity, and that is going to be letter D. And the smallest heat capacity tells me that this 10,000 joules is going to go a lot further to do the indicated thing. So the heat capacity is only 0.4. This is going to change a lot more temperature than this one's going to be, and it's going to be able to produce more mass. Now, if I do those calculations, I do get the fact that this will give me the greatest mass, which is about 125 grams. But look for the smallest heat capacity to do the largest temperature change or have the largest mass to make that change. All right, next one. Look at all the words on this one. For a classroom demonstration, a chemistry teacher put samples of 2 different pure white solid powders in a beaker. I actually did this demo a couple weeks ago. The teacher places the beaker on a small wooden board with a wet surface, then stirs the content of the beaker. After a short time, the students observe that the bottom of the beaker is frozen to the wood surface. The teacher asks the students to make a claim about the observation and to justify their claims. Which of the following is best claim and justification based on the student's observation? All right, so what happened? The temperature went down and the beaker got frozen to the surface, which tells me that it's an endothermic reaction, and the temperature of the beaker and the water on the board decreased as heat was absorbed from the water into the beaker. So that was an endothermic type reaction. Okay. As you're going through these questions, if you want to just continually pause the video so you can read it through on your own, I highly recommend that. And then you can kind of make your guess, and then I'll kind of run through it as well. So we've got a reaction of combustion of methane, looks like, and the delta H is less than 0. Which of the following statements must be true for the combustion of methane? Because it's exothermic, delta H is less than 0. That means, as I'm looking through my choices, that the sum of the bond energies of the product molecules is greater than the sum of the bond energies of the reactant molecules. So those bond energies, we put a little bit of energy in to break them. We got a lot of energy out when the new bonds were actually formed. So next question. We have oxygen breaking apart, looks like, into 2 separate oxygen atoms, which means we have to break that bond. Delta H is plus 495. That makes sense because forming a chemical bond is exothermic, breaking the chemical bond is endothermic. So which of the following best explains why the enthalpy change is positive? It's endothermic because breaking the OO bond requires energy. So that's just a quick one about bond energies. All right, now it looks like we have another one about bond energies. Let's get it in there. Based on the bond enthalpies given in the table below, what is the best estimate of delta H for the reaction? Okay, so remember, a minute and a half, we're going to have to do a calculation on this. Okay, so delta H is going to be bonds broken, and that looks like we're going to have 4 CH bonds, 410. And if If you need to, you might have to just draw the Lewis structure to see what kind of bonds you actually have. And 1F2, that's going to be 160. Get the total on that side, minus the bonds formed, which is going to be 3 of the CH bonds, and 1 of the CF bonds, 490, and 1 of the HF bonds, which is 570. And if I do that math, I get something very close to negative 490, and that means letter B is my answer. So you might have to do a calculation for some of these questions, and I apologize for that. That's just kind of the way things are going to roll. All right, so here's another one. We've got a reaction. Delta H is negative 128. A 0.64 gram sample of calcium carbide. Okay, so they give us that the molar mass is 64. Notice that this is 1/100th of that. That makes per, so we got 0.01 moles. Okay, great. It's added to 100 milliliters of water. All of it reacts. Which of the following is true of the reaction system when that reacts? So we have a bunch of energy either absorbed or released. It's negative, it's going to be released, so it's got to be either B or D. Okay, 0.01 moles times negative 128 kilojoules per mole. That's going to give me 1.28, which is very close to 1.3 kilojoules, and that's released because it is negative. All right, and next one, sorry about that. What is the standard enthalpy change delta H for the reaction represented above? Okay, so I've got 3 of those making 1 of those, and I've been given the heat of formation for both of them. Okay, quick little calculation. Delta H is going to be the sum of the products, which is 83. I'm just kind of penciling this in quickly, minus the sum of the reactants, which is 230, but there's 3 of them. So that means I'm guessing this is about 690. There's 80, so we're looking at a negative 607. All right. Okay, moving on, we get to one that has a data table. You can pause the video and read the whole thing if you'd like. We're given 1 gram of a solid, 2,000 grams of water, and a temperature change of plus 2.1. That positive 2.1 is telling me that it's an exothermic reaction. The heat generated by the combustion is also a clue. So I'm looking probably at one of these negative ones because that gives it exothermic. What's the best estimate of the heat of combustion of the organic solid? Okay, so I know that it heats up some water, so I'm just going to do a quick Q equals Cm delta T. Q equals the heat capacity of water. Let's just do 4.2. The mass is 2,000 grams, and it went up by 2.1 degrees Celsius. So about 8,400. Let's see. And then I divide it by the 1 gram, and so I end up with a couple taps of the calculator, and I get about 17,640, which is about 18,000. 18,000 joules. That's about 18 kilojoules, and that is per the 1 gram that was combusted. So we're looking at kilojoules per gram as our unit for that one. Again, it's an estimate, so just get close and pick the appropriate choice off of that. All right, and we have another heat of combustion. A 1 gram sample of cashew, if you want to check this one out, pause the video and read the entire thing, is burned in a calorimeter containing 1,000 grams of water, and the temperature went from 20 to 25. A 3 gram sample of a marshmallow was burned in a calorimeter with 2,000 grams of water, and the temperature again went up by 5. Which of the following can be concluded about the energy content for 1 gram of each of the 2 substances? Okay, so we already have the 1 gram of the cashew, which changed it by 5. We had 3 grams of the marshmallow, which changed it also by 5, and also twice as much water. So we have twice as much water doing the same thing, but 3 times the amount of mass. So it can be concluded then that the combustion of the 1 gram of cashew does more per gram than the 1 gram of the marshmallow. So there you go. Again, there's a lot of reading on these things. So I think that's half of the battle on an AP exam, just getting through all the content. All right, pause the video and read it if you'd like. The student reacts magnesium and hydrochloric to make these 2 things. And it's important to read the entire question. Sometimes my students miss things because they just go right to the reaction and miss one of the instructions, or they get it opposite. Information about the experiment is given below. 2.4 grams of magnesium, the volume is 300, and so on. The actual question is, if the student conducts a second trial and uses the same mass of magnesium but 500 milliliters of acid, which of the following will occur? And I'm thinking that because we're using a bigger volume, the temperature change will be less because you're heating up more of a solution that's mostly water-based solution. So you'll get the same amount of heat, just less of a temperature change because you're heating up more stuff. All right, another data table. Man, they just keep coming, don't they? Calorimetry experiment is conducted to determine the specific heat capacity of a metal. Okay, great. The results are shown in the following table. So we have the metal, temperature, mass of the water, temperature, the final temperature, heat capacity of the water. Based on the information, what's the heat capacity of the metal? Okay, guys, you're going to have to do a calculation on some of these. And this is, we have two substances in contact with each other. So this is one of those where we're going to have to use that Cm delta T plus Cm delta T equals 0. Make 1/2 the metal, 1/2 the water, and plug it in. And again, you got 1.5 minutes to do this. So, take the time, but do it quickly. So we're going to leave C by itself. I'll move this up here so you can see it better. The mass is 15 grams. The temperature change, let's see, final temp is 20. It started at 80. Heat capacity of the water is 4.184. Mass of the water is 50 grams. Temperature change, again, it went to 20, but started at 18 equals 0. So notice that the water didn't change very much in temperature because it's got a very high heat capacity, and the metal changed a lot in temperature. And if I work this all out on my calculator, I end up with a 0.46 heat capacity, which is somewhere around the heat capacity of copper, but I don't think that's copper. All right, so again, 1.5 minutes, try to get through that in as much as you can. And a quick little tip, if you're doing like an AP exam or an exam in your classroom, you get to a question like that, which you know is going to take you a while, maybe jump past it, get the points on the ones you can do quickly, and then come back to the ones that might take a while. So just a little time management idea there. Okay, so here we have another data table. Specific heat capacity of liquid phase is 4.2, and this is for water. Heat of fusion is 330. A sample of ice at 0 is added to 100 grams of water at 33. The mixture is stirred gently until the temperature of the water is 0. All the remaining ice is quickly removed. Based on the information, the mass of ice that melted is closest to. Okay, so basically we have the heat of fusion times the mass, and the energy it took to melt that is going to be equal to the energy that the water lost. 4.18, we'll use 4.2, just like they said, joules per gram degree. The mass is 100 grams, and the temperature change is 33. Okay, so it went from 33 down to 0. So quick tap of the calculator, 4.2 times 100 times 33. That's 13,860 joules that the water lost as it cooled. That must have gone into the melting of the ice. 330. I was always told it was 334. All right, so divided by 330, and I get 42 grams of ice that probably melted in this particular reaction. So there you go. Moving quickly. You can pause the video and read this next one if you'd like. There's the reaction. Looks like a double replacement precipitation reaction. 10 milliliters of 1 molar and 10 milliliters of 1 molar. That tells me they're equimolar and that both are the limiting reactants. If the final temperature is 35 from 25, what's the value of delta H for the reaction? Okay, this is where you're going to do that. Delta H equals negative Cm delta T over moles. Okay, so heat capacity of water, 4.2 gram degree. Always a good idea to show your work. All right, the mass that we should use. If 10 milliliters is combined with 10 milliliters, That's 20 milliliters. And if I'm estimating 1 gram per milliliter, I'm just going to put in 20 grams of the solution, and the temperature change is 10 degrees Celsius. We're going to divide that by 0.01 liters times 1.0 moles per liter. That'll get me the number of moles on the bottom. So 4.2 times 20 times 10 divided by 0.01 gives me 84,000 joules. And that's 84 kilojoules, but the answer that they gave it to me in joules per mole. So that is my answer on that. I like when things work out. All right, again, look at all the words on these. The reaction represented above goes essentially to completion. Okay, great. Delta H is positive, so that's endothermic. The reaction takes place in a rigid container. Which of the following statements about the bonds in the reactants and products is most accurate? So if it's endothermic, the energy required to break the bonds is bigger than the energy that we get from making bonds. So the sum of the bond enthalpies of the bonds in the reactant is greater than the sum. There it is in letter A. And that would be our answer. All right. And here we get to our next one. And I didn't plan this, but this one is actually very similar to the one we just did. So why don't you pause the video and read this question and see what you can come up with for your answer on this one. And if you paused the video and came up with answer C, then congratulations, you understood what we did on the last one. This one is exothermic. Sorry, delta H is less than 0. So because it's exothermic, the energy absorbed as the bonds are broken is less than the energy released as the products are formed. So we get more energy back from the products than we had to put in to break the reactants. Okay, you might know this already, but there is likely going to be sets of questions that all go together, and they may be referred to the same graph or the same data table or something like that. And this is one of those. Here we have what looks to be like a heating curve. Again, kind of a misnomer. It's more like line segments. We have solid phase, melting, liquid phase, boiling, and gaseous phase. The enthalpy of vaporization of water is 40.7. Which of the following best explains why the enthalpy of vaporization of methane is less than that of water? So this is actually for methane, and its heating curve. So they're saying this is less than the 40.7 for water. Water has a high enthalpy of vaporization because it requires a lot of energy to break those hydrogen bonds that they have with each other, and so it's hard to break them apart. You need more energy. Methane does not have that, and so it's more of a nonpolar molecule with London dispersion forces, so they're easier to break apart, and therefore they have less energy is needed. And so there's A. How much energy is required to melt 64 grams of methane at 90 Kelvin? Okay, so 64 grams is, if you divide by 16, you get 4 moles. So there's 4 moles of methane times 0.94 kilojoules per mole. And that's going to be something just less than 4, and that gives me my answer as B. Which of the following best explains why more energy is required for the process occurring at 110, that's vaporization, than for the process occurring at 90? Okay, why is this segment longer? And that's typical for most things because when you're vaporizing, you're completely separating the molecules from themselves, like completely separating. Whereas when you're melting, you're simply kind of giving them a nudge so they can move around a little bit. And so it requires more energy. And which choice is that? That is going to be choice A on that. Okay, next one. Take a moment and read the question. Pause the video if you need to. Here's a data table with 2 heat capacities and a mass of 1. They're heated from 25 to 75. The change in average kinetic energy of the atoms in the samples is okay. We need laser focus on this one because they've given us heat capacities and we're going on and we're going to think to ourselves, oh, aluminum has a higher heat capacity, so it's going to absorb more heat. And yes, that is true, but that's not the question. The question is average kinetic energy. Because they're going from the same temperature to the same temperature, their average kinetic energy is equal. It's the same. Even though aluminum will actually absorb more heat, it does so to get the same kinetic energy as the iron does. Okay, laser focus on that. Next one, wow, big data table, couple of reactions, delta H for each one. In an experiment, 30 grams of ethane and 30 grams of propanol are placed in a separate container. Each compound undergoes complete combustion. Which best compares the quantity of heat released in each combustion? Okay, so with the same mass, but propanol weighs twice as much, so I'm going to get half as many moles as the propanol. Okay, and half as many moles would give me half the heat, and so the quantity of ethane, the Q from the ethane, is actually going to be higher than Q for the propanol. So it didn't need to do a calculation on that if I can just think through that. Okay, next one. Pause the video and read it if you would like. Which of the following best explains why the combustion reactions in the table are exothermic? Okay, I didn't even include the table on here. The table's not even important. If we know that it's exothermic, then the bonds, the energy required to break the bonds is less than the energy required to form those bonds, and that is choice D. It doesn't even matter what the reaction is. If it's exothermic, that is the case. Ooh, another heating curve. Excellent. And this is for CHCl3. Feel free to mark up your papers and pause the video and read it if you would like. The question is, which of the following best describes what occurs at the particle level that makes segment D longer than segment B? Okay, this is, again, that same question. You'll see maybe that's a hint that they'll be asking you this in May. This segment is longer than B. Okay, why? That's because you're separating the molecules from themselves, separating molecules completely. And that gets me letter D on that. All right. Next one. Which of the following is a list of the minimum amount of data needed for determining the molar enthalpy of solution of KCl? Okay, they ask you questions like this, where you're not doing the calculation. They're just saying, if you've done this lab, you should know the items that you need. So again, if we're doing delta H, we need C, we need the mass of the solution, we need a T final and a T initial, Cm delta T, over the number of moles. Okay, that's my general formula. So let's see, I'm going to need the mass of the KCl, which I'm going to convert to moles. So I do need that. Okay. I do need the mass of water. That's going to go, the total mass is going to go there. Initial temperature, final temperature. Okay. This one has one or the other, but not both. I do need both. So I'm looking down here at C and D. And the only difference between C and D is that this one includes atmospheric pressure. Do I need that? No, I don't think I need that. So that would be letter C for that. All right. Another one, pause the video and read it if you would like. Delta H for this reaction is negative 393. The reaction's shown there. When 3.9 grams of potassium is added to 200 milliliters of water, all the K reacts with the water. Which of the following is true when the 3.9 grams of K has completely reacted? So they're giving us how much energy. Okay, first of all, it's exothermic. So that means energy is released. So I'm looking down here at C or D. Is it 10 kilojoules or 20 kilojoules? Maybe a quick calculation will help. 3.9 grams of potassium. I happen to know that potassium has a molar mass of 39 grams, so we're looking at 0.1 moles. Okay. And if it's 0.1 moles times negative 393 kilojoules per, okay, and here it is, kilojoules for every 2 moles. Okay, so that's about 400 divided by 2 is about 200. 200 times 0.1 is about 20. And so that gives me a rough estimate of about 20 kilojoules released, not absorbed, by that reaction. Next one, pause the video and read it if you would like. A 100-gram sample of a metal was heated to 100 and quickly transferred to an insulated container holding 100 grams of water. temperature of the water rose to 35. Okay, which can be concluded. As we look through the choices, they give us things about the metal temperature change more than the water temperature did, or less. It did change more than the water did, but the metal lost the same amount of thermal energy as the water gained. So yes, they're changing different temperatures, but the heat lost by the metal, should be equal to the heat gained by the water. So equal heat, different temperature change. Ooh, I like this question. This one gives a particle diagram of a solute dissolving in a polar solvent. So we have the solute breaking apart, the solvent also separating from each other to leave these little pockets, and then the final solution is over here. So we have to know this. This is one of the recommended labs, heat of solution. And we have to know that breaking things apart causes and needs energy to go in. That's endothermic. So this is endo. This is also endo, separating the solvent molecules. But the new attractions that are formed over here, those are exo. Forming those attractions releases energy. So steps 1 and 2 are endothermic, and the final step is exothermic, putting them together, solute and solvent. Okay, a 2-mole sample. Check this out. Pause it and read it if you would like. Undergoes the phase transition illustrated in the diagram. Now, what is that phase transition? We've got, looks like gas and then liquid here. So we're condensing on that. The molar enthalpy of vaporization is 38.6, plus 38.6. Vaporization is endothermic. This condensation is now going to be exothermic, because when these lose their energy to go back in the liquid, it has to go out. So I'm looking for a negative value. Which of the following best identifies the change in enthalpy shown in the diagram? Okay, so 38.6 goes in to vaporize it. 38.6 comes back when it condenses, and that's per mole. I'm told I have 2 moles, so double that is 77.2 kilojoules. All right. Based on the information in the table, which of the following substances produces the most energy per gram of the substances combusted? So I got a bunch of heats and a bunch of grams. And so they're saying energy per gram. All I have to do is take the energy divided by the grams and see which one is going to give me the biggest value. And it looks like these are going up slightly. These are going up a lot. 290 divided by 2 is 145. 1900 divided by 16, that's definitely lower than 145. And I'm going to do the same thing here. So the one that gives me the most energy per gram is the hydrogen. All right. A 30-gram sample of aluminum is heated to 50 and placed in a calorimeter containing 150 grams of water at 20. As the system approaches thermal equilibrium, energy is transferred where? So that aluminum is going to have to cool down. The water is going to have to heat up. So the energy is going from the aluminum to the water, and the temperature of the water decreases or the temperature of the aluminum decreases. The aluminum is going to decrease in temperature. So nice one without a calculation. A 1.5 gram sample of ice is placed in a warm room. Which of the following describes the energy transfer involved in melting the ice to create liquid water? So energy has to go in to melt that ice. It's 334 joules per gram, and I'm 1.5 grams. So we want 1.5 times that, which looks like around 501. And the energy is going from the room to the ice because the ice has to absorb it in order to melt. Melting is an endothermic process. All right. Here, you're going to get some that they'll say, don't give us the answer, show us the work, show us the setup that you would use to get the answer. And they give us the reaction and a bunch of bond energies. So remember that bond, the delta H is going to be bonds broken minus the bonds formed. All I need to do is know which ones are broken from here and which ones are formed. And this, don't guess, guys. Make sure you draw the Lewis structure, because just by looking at this, you might think that it's a carbon-oxygen single bond. That's not even shown here. Maybe it's a double bond. Maybe it's a triple bond. We have to know that. And so you might have to draw the Lewis structure and find out that it's a triple bond. Okay? And over here, the oxygen is going to be a double bond. And the carbon dioxide, if you draw the Lewis structure, you'll find out again that it's not carbon-oxygen single bonds or triple bonds. It's a couple of double bonds. So I need one triple, so that's 1072, actually two of them. So two triples, that narrows it down to here. One of the double bonded oxygens, so I'm still looking at either A or B, not these, minus two of these, so four carbon-oxygen double bonds, and that's 799 each. So my correct answer is going to be letter B on that. I don't have to calculate the answer. I just have to pick the appropriate setup. Moving on. Pause the video and read it if you would like. We got two reactions. Based on the information for the two reactions given above, which of the following gives the quantities needed to calculate the enthalpy change for the reaction represented by the overall equation? This is Hess's law. Using a system of equations, we need to get these two to add up to the total, this one, and then we can add up the delta H's. They give it to us in terms of the delta H's. So to get these to add up to this one, N2O4 has to be on the right-hand side, so also that the NO2s can cancel. So I have to reverse this one. That's going to make that negative. And then I'm going to keep this one the way it is so that I get the two NOs on the left-hand side where they should be. So delta H number one has to be a negative value. It has to be made negative. And we keep delta H2 the same. So letter C is the appropriate one there. Again, we don't have to get the answer. We just have to know the process, which is kind of a common theme. Next one, pause the video and read it if you would like. Gaseous hydrogen, gaseous chlorine form hydrogen chloride. We want to know what's the value of delta H. So again, bonds broken minus bonds formed. So the bonds that are broken, hydrogen is 432. That is a single bond, and luckily they didn't give us anything double in there. The chlorine is 239. We're going to minus the HCl, and we're going to do two of those because two molecules are formed. So two of the HCl bonds, 427. And a quick tap of our calculator is going to give us minus 183 on that. This is bigger than this, so we're going to have an exothermic chemical reaction on that. Okay, good. Another one where we don't have to do any calculations, but this is all about Hess's law too, I can tell. The enthalpy change for the reaction represented above is delta HT. Okay, do we have the reaction? Nope, but I don't care. Delta HT that's the overall. This reaction can be broken down into a series of steps as shown in the diagram, delta H1, 2, and 3. The relationship that must exist among the various enthalpy changes, according to Hess's law, if you do it in one step or three steps, energy change is the same. So which one gives us that? And it looks like 1, 2, and 3 subtracted from delta HT should give us a difference of 0. They should be the same. So one subtracting the other should be the same enthalpy of heat. All right, a couple more to go, and then we'll be done speed running these questions. Ooh, this looks familiar. We have oxygen breaking apart into oxygen atoms. The bond enthalpies are there. An equation representing the dissociation of O2 and the bond energies is shown. Which of the following is the enthalpy of dissociation for O2? Okay, if this is the bond energy, and remember O2 is diatomic and it's a double bond if you draw the Lewis structure on that. So we're breaking a double bond. And they put in the single bond in here. And it's kind of tempting that you're going to want to use it, but don't use it. To break this into this, we simply have to put the energy back to break that bond, which is 495. And it's going to be endothermic. So it's going to be a positive 495 on that. The 146 is not necessary because we're not actually forming new single bonds over here. Those oxygens are just going to be separate oxygens, not bonding to anything. And our last question. According to the information above, what is the standard enthalpy of formation for NH3 at 298? So they give us overall delta H, and they want the enthalpy of formation of this one. So remember that the overall delta H is equal to delta H of the products minus delta H of the reactants. Okay, we know what the delta H is, 92. The products are hydrogen and nitrogen. Those are elements. Those have, by definition, 0 enthalpy. So 3 times 0 for the hydrogen plus 1 times 0 for the nitrogen, that just gives me 0. This is a positive 92. So that means the enthalpy of ammonia, 2 of whatever that is, delta HF for ammonia, has to equal 92. Okay, and so this is going to end up being negative 46 because of that negative sign, and we're just dividing that by 2, so negative 46. All right, so we went through a whole bunch of multiple choice questions. We'll summarize here. Remember, you have a minute and a half per multiple choice question. I think we did a pretty good job with our time management on this one. Hopefully that helped. If you need to go back and review anything, or if you have any questions, you can send them to me in the comments about a particular question. I hope found this helpful, and in the meantime, happy studying and have a great day.